everyone, welcome to Mass City Academy, a city of great learning. This is our class on physics and we are taking our lesson 1. Under our lesson 1, we shall be seeing dimension of physical quantities. Okay, we all know about physical quantities. These are quantities that we study in physics, our everyday physics. If you don't remember, let me remind you some. We have force. Force is a physical quantity. We have velocity. Velocity is a physical quantity. We have momentum. Momentum is a physical quantity. Momentum. And so on. All these are physical quantities. Now, before we can go into dimension of physical quantities, we should know that physical quantities are divided into two. We have the fundamental and the derived. Now, I would like us to understand that the difference between the fundamental physical quantities and the derived physical quantities is based on their unit of measurement. What do I mean by this? Let's talk about the fundamental physical quantities. When we talk about fundamental physical quantities, we say that they are divided into 7, which are length, and length is measured in meters. Let me use this. We have mass. Mass is measured in kilogram. We have time. Time is measured in seconds. We have electric current. Electric current is measured in ampere. We have luminous intensity. This is measured in candela. 1, 2, 3, 4, 5. Remaining 2. We have amount. This is measured in mole. 1, 2, 3, 4, 5, 6. Remaining 1. We have length, mass, time, electric current. We have temperature. This is measured in Kelvin. Now, these are called the fundamental physical quantity. They are fundamental in the sense that their unit of measurement is unique to them. They are not borrowed. They are unique to them. Okay, let us look at the derived one. We said that when the unit of measurement of any physical quantity is a combination of one or two or more of the fundamental, then that physical quantity is called a derived quantity. Let's take an example. Velocity. It's measured in meter per second. Now, if you observe, the unit of velocity is meter per second. Meter belongs to length and seconds belongs to time. So that means velocity combined m and s to get its own unit, meaning that velocity is a what? Derived. While length did not borrow m from anybody, time did not borrow s. It's unique to them, it's their own. But when a physical quantity collects one or two or more of the units of the fundamental, that physical quantity is called derived. Let's see another one. Let's look at force. Force is a derived. Why? Remember that it is a kilogram meter per second square, which is called Newton, which you call Newton. Okay, you see that the unit of force is kilogram meter per second square. Watch now, kilogram was borrowed from mass. Meter was borrowed from length, and time, the seconds from time. So force is derived. Why all this? Now we have said that as a matter of fact that fundamental quantities are only 7. But the derived quantities are many. They are not numbered. They are many. Of all the physical quantities in this world, only 7 of them are fundamental. And we have told you that the difference between the fundamental and the derived is based on their unit of measurement. If it is unique to them, it's fundamental. If it is derived, then it is if it is combination of one or two of these, then it is what called derived quantity. Okay, having known about fundamental and derived quantities, then we go to dimension analysis. What is dimension analysis? Dimensioning of a physical quantity. Let me use this definition. Dimensioning of a physical quantity is defining all physical quantities based on the basic fundamental quantities. I repeat, dimensioning of a physical quantity is defining all physical quantities based on the basic fundamental quantities. Now, I go back. I said, remember that I said that the fundamental quantities, we have length, we have mass, we have time. Of the 7 fundamental quantities, I brought out only 3. These ones are called the basic fundamental quantities. Basic. In exam, if you are asked, which of the following is a basic fundamental quantity? We need only these 3. But if you are asked, which of the following is a fundamental quantity, then there are 7. Meaning that basic fundamental quantities are 3, while the fundamental quantities in all are what? 7. Okay. Now, defining all physical quantities based on this basic fundamental quantity is what we call dimension. Now, first of all, we are going to dimension these 3 basic physical quantities. The dimension for length is going to be L. The dimension for mass, we use it as M. Dimension for time, we use it as T. Now, if you observe, dimension for length is used as L, meaning that the first letter from length was used. Then you put this block bracket to show that you are doing dimension. Dimension for mass, the first letter here is M, we have put it. Dimension for time, the first letter here is T, we have put it. So, when we define all physical quantities based on these basic fundamental quantities, what we are doing is what? Dimension analysis. Okay, let's take some few examples. Let me take from my book. Let's take some few examples. I want to take, let's start taking some few examples of fundamental quantities. Let me take a dimension of area. Now, one good thing you should understand is, for you to be able to find the dimension of a physical quantity, you need to know the unit of that physical quantity. It will help you to get the dimension of that physical quantity. Let's talk of area. Now, area is measured in meters square. Area is meters square. Okay, if the unit of area is meters square, then what is the dimension of area? I will go to this unit of measurement, meter. I will now ask myself, in the basic fundamental, which of them can be allocated to meter? We say that it is length. So the dimension of area becomes length square. This becomes the dimension for area. I believe that was very clear. I take another one. Volume. Remember that dimension for volume is meter cube. As a unit of volume is meter cube. So each dimension, since it is meter, it is length, then the cube. This becomes dimension for volume. This becomes dimension for volume. I hope we are following this. Let's take another one. Dimension for velocity. Dimension for velocity is, unit for velocity is meter per second. This is the unit for velocity. So for me to get the dimension from the unit now, I'll ask myself, this is meter. In the basic fundamental, meter belongs to length. So I have L up. This is seconds. In the basic fundamental, seconds belongs to T. I put my T and block it. And this becomes dimension for what? Velocity. Or it can be written as LT minus 1. When you recognize indices, meaning that whatever is down can come up to become this. Okay. Let me take another one. Force. Force. What is dimension for force? Remember that force is measured in kilogram meter per second square, which we also call Newton. Now, what is dimension? Now, I want to get this dimension. Kilogram in the basic fundamental belongs to mass. So I'm going to be having M there. Meter belongs to L. Length, which is length. Seconds belongs to time. And this becomes dimension for force. MLT minus 2 becomes dimension for force. I believe with these few examples, we can form dimension for any physical quantity which we wish to obtain. Let's take another one. Density. What is dimension for density? If density is mass, over volume. Density is mass over volume. So each unit will become kilogram over what? Meter cube. Kilogram over meter cube. So the dimension becomes kilogram belongs to M and meter cube belongs to volume, meter, L cube. So I'm going to be having each dimension to be M over capital M, capital M over L cube, or M L raised to minus 3. This becomes dimension for density. That becomes dimension for density. We'll take another one. Momentum. Dimension for momentum. Momentum is mass times velocity. So, unit for mass is kilogram. Unit for velocity is meter per second. So, this becomes the unit for momentum. The dimension becomes kilogram is capital M, meter, L, time, T raised to minus 1. And this becomes dimension for momentum. What of impulse? Dimension for impulse. Impulse is force times time. And each unit becomes force, kilogram, meter per second square, dot seconds. Okay? And that will produce kilogram, meter per second square, minus 2 plus 1 will give me minus 2 plus 1 will give me minus 1. This becomes unit for impulse. So the dimension becomes kilogram, M, meter, L, time, T, minus 1. Okay, I think we have taken much example for dimension of some physical quantities. Note, when the unit of two physical quantities are the same, their dimensions will also be the same. I repeat, when the unit of two physical quantities are the same, their dimensions will also be the same. What am I trying to say? Look at the dimension for momentum, MLT minus 1. Look at the dimension for impulse, MLT minus 1. It means that the unit of momentum and that of impulse are the same. Hence, momentum is equal to impulse. I repeat, when the unit of measurement of two physical quantities are the same, or when two physical quantities are equal to each other, they will have the same dimension. Look at the example of momentum and impulse. Momentum is equal to impulse. This is the proof because they have the same dimension. And they have the same unit of measurement. Observe that. So they will have the same dimension. On this note, I'm going to say some other things. Let us see. Dimension for energy. Energy. What is energy? Energy is the rate at which work is being expanded. Okay? Okay. Now, if I'm to ask dimension for energy, remember I have kinetic energy and we have potential energy. Whichever is their dimension, remember that kinetic energy is measured in joule. Potential energy is measured in joule. And it is a unit of measurement that determines the dimension of a physical quantity. Since this one is in joule, this one is in joule, energy is also in joule. These two are types of energy. So they will all have the same dimension, just like I've said. Now let's say something. Kinetic energy is given as half mv squared. There's something I want to say about this half. One of the limitations of that kind of dimension is that it cannot be used to find the expression for a constant. I repeat, dimension analysis cannot be used to find expression for a constant. What do we mean by constant? Numbers, 5, 10, 15, 100, 1 million. All these are quantities. are constants. We cannot use dimension analysis to find expression for them. So this have no expression in dimension analysis. So let me go on. But I have meter, we have mass times velocity. This is not meter here because kinetic energy is mass times velocity. Remember that. So mass, the dimension for mass is what? Capital M. Now the dimension for velocity is LT minus 1, then all squared. This brings me to M. These two belongs to both of them. Hope you remember your indices. I have L squared T minus 2. Are we there? So dimension for kinetic energy becomes M L squared T minus 2. That is dimension for kinetic energy. ML squared T minus 2. Now, we want to also find dimension for potential energy. If it doesn't look like this, then this is not equals to this, since their units are the same. Okay, let's see. For potential energy, it is mgh, mass times acceleration due to gravity times height. Okay, what is dimension for mass? It's capital M. What is dimension for acceleration due to gravity? Acceleration is LT minus 2. What is dimension for height? It is length, which is L. So if I multiply all this, I'm going to be having M. I have L times L will give me L squared. Then I have T minus 2. That becomes dimension for potential energy. If you observe, the two dimensions are the same. It means that because their units are the same, so they are going to have the same dimension. Both of them as what? Energy. So if I'm asked to find the dimension for energy, I can get it from the dimension for any of this type of energy. I believe that was very clear. So at this point, you can be asked in a competitive examination and say, find the dimension for initial velocity. Find the dimension for initial velocity. Remember, we used to use V as final velocity and it's measured in meter per second. You use U as initial velocity, which is also measured in meter per second. Because the V velocity is measured in meter per second and the U velocity is also measured in meter per second, then we have the same dimension. We have said that. So dimension for this one is LT minus 1. Dimension for this one will also be LT minus 1. So whether they ask you find dimension for initial velocity or final velocity, they are the same. Velocity is velocity. Energy is energy. Impulse is equals to momentum. They have the same dimension. At this point, I believe we have really understand how to get dimension for different physical quantities as we have measured. Then I would like to drop us with this point. Note this. When two physical quantities are added together or subtracted from each other, they will have the same dimension. I repeat. When two physical quantities are added together or subtracted from each other, they will have the same dimension. Let's take this example and we'll see how this is being used. Okay, I take this one example. Okay, they say that consider the equation P plus A over V squared into V minus B is equals to RT. Consider this equation. The question says consider this equation, which is equation of gas. This is equation of gas. If P is equals to pressure, T is what here? 10 pressure. V is volume. P is pressure. V is volume, R is gas constant. Now, the question now says, find the dimension of A and B. Find the dimension of quantity A and that of what? B. So we are looking for the dimension of this and this. This is a question. So we are going to, let's write. Now, I've said it before that when you look at an equation, you see that P was added to A over V squared and V was subtracted from V. The law says that when two physical, this is a physical quantity and this is a physical quantity. This is a physical quantity and also this is a physical quantity. When two physical quantities are added together or subtracted from each other, then their dimensions will be the same. So, I want to get the dimension for A. Solution. Since P was added to A over V squared, that means the dimension of P should be equal to the dimension of A over V squared. This dimension should be equal to this. So since I know that the dimension of this should be equal to this, I'm looking for the dimension of A. I will first of all make A subject of the formula. So I will make A becomes PV squared. A becomes PV squared. That means for me to get dimension of A, if I multiply the dimension of P with that of V squared, I'm going to get dimension of A. So at this point, A becomes, since P is pressure, dimension of pressure, remember, pressure is equals to force over what? Area. Dimension for force is MLT minus 2. I hope we still remember that. While the dimension of area is L squared. I hope we still remember that. So if I have this over this, there is 2L down and there is 1L up. This can take away this. That means dimension for pressure becomes M L raised to power minus 1 T raised to power minus 2. This becomes dimension for pressure. So I bring it here. M L raised to power minus 1 T raised to power minus 2 times dimension for velocity. Then they say this is volume. They say this is volume. So dimension for volume is L cube. Remember it was raised to 2. Remember it was raised to power 2. So analyzing this properly, we have L, we have M. There is this will give us, let me explain this very well. We have M, L raised to power minus 1, T raised to power minus 2, then times L raised to power 6. I believe we understand that 3 times 2, 6. This is now more simplified as M, L minus 1 plus 6 will give me 5. Then I have T minus 2. This becomes dimension for A. I've answered the question. They asked me to find dimension for A. Now, for proof, let's see if it is true. If dimension for pressure, is M, L raised to power minus 1, T raised to power minus 2, if that is dimension for pressure, then the dimension of A divided by V squared should be equal to the dimension of pressure. As we have proven, say, when two physical quantities, this one physical quantity, this another one, when they are added together, they should have the same dimension. That means the dimension of the whole of this should be equal to the dimension of the whole of this. Now, since I've gotten that of A to be this, so A over V will give me A is M L raised to power 5 T minus 2 over V squared, which is L raised to power what? 6. This becomes, this 6 goes up. We have M L 5 minus 6 T minus 2. 5 minus 6 will give me minus 1. M L minus 1 T minus 2. So the dimension of A over V squared is this, and which is the same thing as this. If you observe, the dimension of A over V squared is equals to pressure. Why? Because both of them was added together. So this is a proof. If I do this by this square, I'll get this. Again, the second question says we should find the dimension of B. I believe at this point we already know what is going to be the dimension of B. B was subtracted from V, and they said V is volume. If V is volume, and this dimension is going to be L cubed, therefore, the dimension of V is equal to dimension of B. Therefore, dimension of B is also L squared. Final answer. The dimension of B will be that of dimension of V. Dimension of P will be that of dimension of A over